So in this video, we'll do an example of the method of integrating factors using the shortcut. And so first of all, let's start off with an example. We have a river with sulfur entering, and we're going to assume that the rate at which the sulfur enters in is, first of all, we have water entering at a rate of 150 cubic meters per day, and we have 2 milligrams of sulfur entering per cubic meter of water. Furthermore, we have 100 cubic meters per day exiting the river. So we have water accumulating in the river since there is more entering than coming out. And as a result, we will have an increase in our volume term. So that number and that number suggest that at any given time inside of this tank, there are S milligrams of sulfur. That's a variable quantity because of the fact that not all of what's entering is exiting instantly, and therefore we get a little bit of an accumulation, a saturation of the sulfur. And so S represents the milligrams of sulfur, and specifically that's in the tank or in the river. And then we have our independent variable, which is T, which is time in days, and that's going to be since the sulfur began entering the river. So next thing we need to know is, let's build a model. So we have a of ds dt equals 300, which is 150 cubic meters per day times 2 milligrams per cubic meter, which gives us 300 milligrams per day. It's got to be in milligrams per day, minus, in this case, we have the 100 cubic meters per day times S milligrams over 500,000 original gallons plus 50 gallons additional per day times the number of days, milligrams per cubic meter. And so here's our what we call our initial value problem. Here's the model, and then we could do a little bit of reduction, which will just make the integration a little bit easier if we factor out a fact 50 from numerator and denominator. And our initial condition, the amount of sulfur at time 0 is 0 milligrams. So that makes things a little bit easier to work with. All right, so the method of integrating factors states that if our differential equation is of the form a of ty plus b of t, so key things to remember here is that a of t is a function of t, b of t is a function of t, y is raised to the first power, it's not the denominator, this is a first order linear differential equation. Now this, it turns out that b of t has to do with the homogeneity, but for now we'll just treat this as just a general first order linear differential equation. It says that if you can write your differential equation in this form, then the solution is y of t equals 1 over mu of t times the integral of mu of t times b of t. All right, so a of t, b of t is this component here. That's why it's so important to identify, where the factor, this is actually called the integrating factor. This is the integrating factor. The integrating factor is equal to E, Euler's constant, to the raised to the power of this whole thing here, negative integral of a of t dt. Okay, so the first step is always to write it in this form, identify what you have, and then the integration follows from that. Okay, so in our model, we have if we express ds dt in a little bit more of a careful form, my S term, which is the second one actually involving the outflow rate, is actually negative 2S over 10,000 plus T. And so if I write it this way, and I basically pull the S out, negative 2 over all that, plus my 300, which is my inflow rate, then I see that my function is clearly of this form, a of t, a function only of t, times my y, which is my dependent variable, which in this case we're calling s, plus 300, which in this case is the b of t component. Okay, so I've got that problem set up, and so now first of all I'm going to calculate mu of t, and mu of t equals e to the negative integral of a of t dt. Well, a of t is going to be my negative 2 over 10,000 plus t. Okay, and that's with respect to t. And I can do a little bit, I have to do a little bit of integration here. It looks scary, but I can factor out a -2, which makes this e to the 2 times the integral of 1 over 10,000 plus t. And that's with respect to t. So if I integrate this, this will become e to the 2 times the natural log of the absolute value of 10,000 plus t. All right, now it's tempting just to cancel out the e in the natural log, but a property of ln, of natural logs, of logs in general, logarithms, is, in particular with natural logs, since that's what we're dealing with, is that if you have the natural log of some quantity squared, we'll say the natural log of, or not squared, but a to the b, then that's the same thing as taking the natural log of a and multiplying that result by b. So people often think about this as, the b sort of can become a factor of the natural log of a. Well, we need to use this in reverse. We need to go from what we have here, which is this, to putting the factor of 2 as an exponent. Now, this must be done, otherwise we end up with some pretty funky results. And you can always try to see if, for example, the natural log of 2 to the third is not going to, or sorry, take this back. If you take e to the 2 ln, let's say 3, and you compare that to, let's see, 2 times 3, which is the temptation of just canceling out the ln's, you're going to find out that e to the 2 ln times 3, if you do that in your calculator, you're not going to get the same thing as when you do, 2 times 3, which is 6. You won't get 6 out of this. E is an irrational number. You're raising it to an exponent. You're not going to get that. So we can prove or disprove by example that these two things can be canceled out. So now I can cancel those out, and I get 10,000 plus t quantity squared. So that is what mu of t is, and now I have my integrating factor. And now all that remains is, in the next slide, we need to now calculate y of t, which is 1 over mu of t times the integral. So we have to do another integral times mu of t, or of mu of t times b of t with respect to t. Now, you cannot simply cancel out the mu of t, otherwise we would have done that early on. It's a function of time that gets reciprocally multiplied in the front of the integral, and then you have a mu of t that needs to be integrated. So it's not a constant that you can move it in and out. Otherwise, we would just move mu of t and b of t out, and then we wouldn't have to integrate anything but a constant. So now this comes out to 1 over, let's see, so we had 10,000 plus t quantity squared times the integral of 10,000 plus t quantity squared times b of t, which was, if you recall, that was 300 with respect to t. Now, this is not a terribly, horribly obnoxious integral to take because I can factor out the 300 and make this 300 over 10,000 plus t quantity squared times the integral of 10,000 plus t quantity squared. Now, obviously, it would be nice if we could cancel those out. That would make the math really simple, but we'd end up with a very, very strange function for the situation. Now, how do you integrate that? Well, most integral sheets don't have something specific for this, but we would have to use we could use a quick u sub. And so if you let u equal 10,000 plus t, then we have the integral of u squared. Now that means du is equal to the du dt, the derivative of the u function, is equal to just 1. A derivative of 10,000 is 1, derivative of t is 1, and so we get du equals 1 dt. Okay, so that means for dt, we can replace that with du, because dt is equal to du. And so I'm not going to copy this thing down. I'm just going to put an arrow here so you don't forget it. Now, the integral of u squared with respect to u is 1 over 3 u to the third plus c. So with the integrating factor, we don't need to do a plus c because as you'll learn in another video, mu of t is just a factor that makes this solution possible, assuming you can do that integral. Okay, well now that we've done the integral, we have a plus c here. Now we have to take that whole quantity and multiply it by 300 over 10,000. I've got an extra zero there. Plus t quantity squared times 1/3. Well, now I can substitute u back in since I've done the integration. 10,000 plus t to the third power plus c. What is important is that this factor right here is multiplying both terms in the parentheses, the constant as well. Because remember that it's 1 over mu times the integral of all that stuff, and the integral of all that stuff is this whole quantity here. So what I have to do is I have to multiply it to the first term, which is 300 over this times 300 over 10,000 plus t quantity squared times 1/3 times 10,000 plus t to the third plus 300 times 10,000 or over 10,000 plus t quantity squared times c. All right, now you cannot just call this C1 or C2 because of the fact that this involves a variable expression. A constant times a variable expression is no longer a constant. So I can do a little bit of arithmetic here. So 300 over 3 will be 100. And oh, this is beautiful. I have 1 over 10,000 plus t quantity squared times 10,000 plus t cubed. So that will just leave me with 10,000 plus t to the first power. So that this cancels out. Two of these factors cancel out. I'm left with that plus, well, 300 times c, that's just a constant. So 300 times c I can turn into c1, but that is all over 10,000 plus t quantity squared. All right, otherwise, if you would recombine this into a constant or not factor this in, you would just have a linear function. And that's why I said it wouldn't make sense, because we know that things do not happen very linearly, especially when you're dealing with something complex as water volume changing and concentration changing. And okay, so that means y of t, our final answer is, well, actually I can do a little bit of arithmetic here. In fact, why don't I just write this as C1 over 10,000 plus t quantity squared. I can distribute this in, so then I have plus 100t plus 1, 2, 3, 4, 5, 6 zeros, so that's 1 million. And now I can go about solving for C1. So C1, under the condition that at time 0, sorry, this is S of t. I keep just going back to the original. So S of 0 equals 0, which means that this side equals 0 when t equals 0. So then I have 10,000 plus 0 squared, which is just 10,000 squared, plus 100 times 0 plus 1 million. And so that term goes away. That term I can subtract over, and I get negative 1 million equals C1 over 10,000 squared, which I'll just write that out real quick. 10,000 squared will leave me with 8 zeros, I think. Yep. 8 zeros, 4, 5, 6, 7, 8. And then when I multiply both sides by that, I will have 1, 2, 3, 4, 5, 6. I will have negative 100 equals C1 if I've done that math correctly. And so now I have my arbitrary constant, and now I can go to something like Desmos, and I can graph this and see if this makes sense. Okay, so I actually goofed. I divided instead of multiplied, and so C1 should actually be this astronomically large negative number, negative 10 to the 14th. And a good way to check that is to actually plot it and see that here's S of x, negative 10 to the 14th, all of that stuff, and I can see that S of 0 equals 0. There it is. There's the sulfur as a function of time. Now, as x approaches infinity, we should note that this thing becomes pretty linear because this term approaches zero. And so as long as the volume changes, the sulfur will increase.